Hi everybody, welcome back to Chem 131. I just have to stretch for a second. Alright. Who's ready for more? More about alcohols and phenols and ethers and all these good things. Maya's ready. Yes, she is. Alright, Maya, you can say hi now. Hi. Say hi. There you go. Yeah, chapter 14 is pretty bad, and it only gets worse, unfortunately. 15 is 15 and 14 are very similar. It's just they cover different topics. Yeah, let's just get right into it. Nothing really new to talk about other than down at the bottom there. There's stuff due today. There's a lab due tonight and a quiz due tonight. So those are soft deadlines, so you still do have an extra day if you need it. Maya says hi. Hi, Maya. She might have said hi. I can't hear her now with my headphones on. That was a tiny meow. Yeah, she's meowing. I'm not even on the right screen here. Let me get to the right screen. So, yeah, get those things in today, and I will try and grade them as I can. Are you doing the exam this week? I have to ask you guys about that, because you have a quiz for Chapter 14, and then you have a test on the material, too. We might push it back a few days. I'm going to make a poll. Maya really doesn't want to do the exam, do you? No, you don't want to take the exam, do you? No. Maya's on your guys' side, apparently. She started meowing like crazy the second I said exam. I'm gonna post a poll to see how many people want to do it on Friday and how many people would rather do it on Monday of week 6, because if I can do that, then I can give you the quiz, because we're gonna finish chapter 14 this week. I can give you the quiz, but I can set the quiz deadline to be earlier, so instead of a week to do the quiz, you'd have like 3 days. And then I could open the quiz so you could see the answers, and then the exam would come out. The issue with Monday is that you still have a lab lecture on that day, but in reality, it's a lab lecture. Watch the video later. I'm going to talk about it anyway, right? How hard could it be? Work on the exam. So, I mean, that's a totally reasonable response, in my opinion. But I do want to be democratic about it. Like, obviously, the cat is only one vote in a class of 30, huh? No, she says she's all the votes. She also votes for hugs. I could go for hugs. Yeah, that sounds good. And nap time. Honestly, Maya for president. She sounds like she knows what's up. And shoelaces. I don't know if I'm a big fan of shoelaces, but Maya really loves them. Anyway, that's what's coming up. I will post an announcement on that. Maya for president. I will post an announcement of that and the straw poll once I make it. Let me write up myself a note to do that, actually. Let's see here. Straw poll for exam date for 131 and 161. Because 161's in the same boat. 140, their exam is just Monday, because they have a Tuesday, Wednesday, Thursday class. So I just put theirs on Monday. But if I put them all on Monday, then that's fine. It gives me more time to write the exam, too. Alright, so let's talk about phenols. We've already talked about phenols. Like, you have seen what they look like. You could recognize them. There is a lab that deals with them next week, I believe. But there's a few other extra things that we want to talk about. So, if you've ever smelled that, what I call the hospital smell, you have probably smelled as Lysol or phenol. Lysol is a phenol, which is why it sounds like the molecule it's derived from. So, phenol is just a benzene ring with an OH group on it. I think I put... Yeah, there's a picture of it. It's a disinfectant because it's slightly acidic. So its pH is less than 7. It's not that much less than 7, so it won't kill people. Otherwise, breathing it would be really bad, and you'd have to ventilate an area very well after you Lysol it. Why am I getting messaged? Oh, I didn't actually put streamer mode on. Hold on. I'm getting pinged from the Discord channels because there are 3 of them. Streamer mode on. There we go. Now I can't hear that. Sorry, I'm like super ADHD from this whole pandemic thing that now like anything breaks my concentration, which is why I have to scare the cat away. She starts meowing at me. Alright, so what does it mean to be acidic? Well, acidic things will donate H plus into the solution. So what that means is that on here, here's my H plus. If it reacts with water, I could just pass this over to here, and I'm going to guess that this thing, yeah, there it is. My H plus that was on the hydroxide group there gets passed over to water and is now an acidic proton, which is what H3O plus represents. This right here could take an extra H plus if there was one. So in reality, this happens, and so you could go back and forth between these. Now, because it's a weak acid, you have mostly this side. Very little of the deprotonated form exists. That's our review for 121. Oops. What do we use phenols for? The most common one is Lysol. The other uses for phenols, though, are as a functional group that you can use for chemical reactions. So, for example, when you synthesize aspirin, let me find the structure of aspirin here really quick online. So, acetylsalicylic acid structure. Because it has a phenol group in it when you start the reaction, and then you esterify it. So let me get... There we go. So we'll copy this. And if I paste it here... Wow, that's great. I pasted a molecule, and I got a black square. I just thought I'd show you that before I went psi. What if I copy this one? To esterify means that you are making an ester. Wow, nothing works today. Everything is terrible. Hold on. Can I copy this image? There we go. Okay. All I was trying to do is get the molecule. Alright, so an ester, which you should know because it's in that page on functional groups. An ester is anything that looks like this. See, that's not a pen. My goodness. C double bond O, O, and then R over here and R over here. And so here's one R, and then this could be the rest of another R. So this right here is my ester. But before we did that, oops, I didn't mean to actually erase part of the structure there. I thought it would put it on a new layer here. But before we do that, you could probably see that this could come from, I don't know, maybe this molecule, right? And it turns out it totally does. To make aspirin, you put this molecule together with this molecule. And then what ends up happening, we're going to do ester chemistry, I guess. This is the next chapter, is you make water and then you link the two. And so that's called esterification. You make an ester. But phenols can be a common group that are used to make esters. And so we're going to see this again in the next chapter. And we actually make you do this experiment in the laboratory if we were doing this on campus. Normally we would have like 6 or 7 labs. I've only picked 5. I'm trying to pick the labs that aren't a focus on make this thing, because it's not very exciting when you don't get to make the thing. But those labs do exist. So whenever you name a phenol, and this is sort of going to be the theme for the day, if you have a cyclic sort of structure and you're going to name any of these things that we're naming today, you put the important group, in this case that's the OH, on position 1, and you always do that. Okay, so if I have... Oh, and then you number it the same way that you name for any ring cyclic compound. You number it so that you have the lowest possible numbers, and then you alphabetize it and extend, so on. So we know the rules by now. So let's do an example and name this phenol. So the phenol always has to be at position number 1. We're not even going to number our phenol. We're just going to assume that it's at position 1 and just write phenol. So what that means is now I got to number the other positions. So we would do this. And so I have, what are my groups? I have 2, 3 dibromo. And then it's a phenol. So we go phenol. And there you go. So instead of calling it a benzene, you just call it a phenol. No problem. Always number it such that the OH is at position 1. And you're all set. All right. I'm going to give you an example to try. Type your answer in the chat when you're done. Now remember that whenever you have 2 groups on a benzene ring, you can use ortho, meta, and para. So this is a thing that you can do with phenols. And then you don't even have to number it. You just have to label it with the correct letter. But what is the correct letter? Is it OM or P for this? Tell me the name of this in the chat. And we'll go over the answer in like 1 minute. Once I go get my phone, because I had to charge it. All right, so what's the answer? Type it in the chat, or Maya will meow sadly at you. Yeah, just like that. O, ethyl phenol is correct. Oops. The O is for oops. I bonked Maya on accident when I reached over to pet her. I tried to pet her head, but her head was higher than I thought it was, and I wasn't looking at her. So now she's just annoyed with me. I'm sorry, okay? Anyway. My pen didn't select. There we go. All right, so if this is position 1, that's not the color I want. And this is position 2. So you could call this 2-ethyl phenol. Or because they are 1 space apart, you could call it ortho. Not... Yeah, I can't spell ethyl, apparently. Phenol. There you go. Either of those is correct. Remember that ortho is 1 space apart. Meta is 2 spaces apart. and para is 3 spaces apart, or directly across. The way I remember that is I write omp. I just count the spaces. All right, that's it for phenols. Nothing very exciting there. Ethers also not very exciting. Ethers are just sort of a dead end in chemistry, it turns out. Ethers aren't reactive. They're kind of like alkanes, but they're super flammable. They're a little bit polar. They're more polar than alkanes are, but they're not super polar. So let's talk about what an ether is. An ether is any molecule that fits the following conditions. There's a bunch of hydrocarbons on both sides of an O. So here I have 2 different sides of my ether are shown here. And so on this side is just methyl. And this side is ethyl. And to name ethers, it's very simple. All you do is arrange the names alphabetically and put a space between each one. In fact, IUPAC naming is... I'm not even sure if there is really an IUPAC naming scheme for these that is broadly accepted. Like, everybody uses common names for ethers. And so what we would call this is just ethyl methyl ether. I'm sure there is an IUPAC naming nomenclature. It probably has to do with methoxides or something like that. Now, if you have the same group on both sides of the ether, you don't even need to include di. You just name one of them. So, for example, if we had, say... Oops, that didn't work correctly. There we go. So if I had this molecule like this... So this is a propyl group. And this is a propyl group too. So you don't have to say dipropyl ether. You could just say propyl ether. And sometimes you see it written like that. Either of those is fine too. And that's as far as we're going to do with ethers. We're just going to say that that's how we name them. Because, to be fair, ethers aren't very exciting. They don't really do anything, but they are fairly common. So here's some examples. What I want you to do is find the groups, name them alphabetically, and then put a space between each word and write ether. Hooray. If the groups are the same, you just write the name of the group once. So go ahead and name these ethers. And then I'll tell you the story about how I almost destroyed the University of Washington 3rd floor chemistry department. Hint, it involves ethers. Yeah, so if you only list one name, you don't have to write di. Because if you wrote, like, say, ethyl ether, then it's assumed that both groups are the same. Now, some people just say it out of habit, and so, because these are common names, ethyl ether and diethyl ether are exactly the same thing. Because you have to have 2 groups. You can't just have nothing on the other side. If it was an H, it'd be an alcohol. And if it was nothing... What am I hearing? I'm hearing, like, crazy cat noises. Go ahead and name these. I'm going to go figure out what's going on. All right. I don't know what my other cat was yowling about. He's probably just bored. He wants to go outside, but it's like 40 degrees. I'm not letting him outside. All right, let's name these ethers. So this is a phenol, and this is a methyl. So this ether would be methyl phenyl ether. Hooray! So then we got ethyl, propyl. So this is ethyl, propyl, ether. And then down here, these are both isopropyl groups. So we'll just write isopropyl ether. There you go. The most common ether by far is this one. It looks like an emote. You got the carrot eyes and then the mouth for the O. So if you do this, I don't know. When I was a kid, this was a popular emote. In the early days of the internet, everybody would type that. And now I know that they were secretly trying to convey to me ethyl ether was what they were trying to tell me. Anyway, this is a really common laboratory solvent. And as we're going to learn on the next slide, I'll just put it on the bottom here. Ethers are ethers are super flammable. In graduate school, I did a lot of chemistry in ethers because they contain an O, so they solubilize some things that are polar. And so some stuff that I was working with for a reaction was soluble in ether, so I would use that as my solvent. And then what you'd have to do after you do the reaction, when you've mixed something together and done a reaction, oftentimes you want to isolate the stuff that's in there and then run it through a column or whatever. And oftentimes what you have to do is you have to remove the solvent. So you have to get rid of the ether somehow. So what I ended up doing, we'll go back to this slide real quick, and then I'll click over here. The way that you do that is it's called a rotovap. And so you have this device that has a circular container that's in a stand that can put you put water in here or something. And if I had drawn it correctly, this circular flask that you connect here, so here would be my solution. So here's my ether. And what ends up happening is that this is all connected to a vacuum. And so ethers, which have a very low boiling point, would then escape and then get trapped in this solution once, because there's frozen stuff somewhere here to capture it. And so ether plus other stuff, and I want the stuff. This is what I want. I don't want the ether. So the ether goes this way. Presumably. Now, this assumes that your system doesn't have any leaks in it. In order to open this, you do have to open a valve, which cancels the vacuum and lets air go in there. And also, when you're hooking this up, this is all exposed to the environment and the atmosphere. And ethers are really volatile, so they're always evaporating like crazy. So, in our laboratory, this was on a bench on the counter. Now, approximately over here, on the same counter, was a buddy of mine who had a Bunsen burner because he was doing something that required open flame. All right. So social distancing was not a thing back then, but we were about 5 feet apart because, we like to give each other our personal space. So I go right up to the rotovap to hook this up, and he's sitting there turning on the Bunsen burner, and he's like, "Oh, what are you doing?" "Oh, I'm pulling pipettes with the Bunsen burner." "What are you doing?" "Rotovapping ether." And we look at each other and we look at our experiment that has not exploded yet, but could have at any moment. He turns off the flame, I set the flask down, and we both walk away very quickly. And we say, never speak of this to anyone again. Because what would have happened is, if this had caught on fire, I would have blown up the entire laboratory. Like, the explosion that I would have made, even with only like 250 milliliters of ether, would have been so big that I would have died. And so would my friend and anyone within like a 20-foot radius of us. So be very careful with ethers if you're ever working with them, because they are super, super flammable. I know of somebody who was working with a bottle of benzene at UC Irvine. I just apparently like am very close to places that are explosive, I guess. I don't know. Somebody was trying to distill benzene, which is also very flammable. And when you distill it, you basically have it over an open flame in a sealed container. But if there's a leak, then that catches on the benzene catches on fire and explodes, and everything blows up. That happened not while someone was in the lab. They just were leaving it to go on its own, and it blew up an entire floor. Like, the whole lab and then the adjacent room next to it just exploded. All the windows blew out. There's smoke pouring out of the building. That was right before I got there, because when I had gotten there, the lab was super new. And I was like, wow, this lab is so new compared to the other lab. What's the deal? And it was because it had just blown up. Let me see here. UC Irvine, Frederick Rhines Hall fire. 2001. Yeah, I started at UC Irvine in 2002. Let me see if I can get a picture of this for you. I mean, this is not much of a picture, I guess. But, so I want this over here. Yeah, so this window right here was approximately 40 feet, I would say, from where the explosion happened. But yeah, it's on there. I'm trying to find a better picture. Yeah, but it was in the Evans lab, and the Evans lab happened to be where I ended up working. William Evans was my 163 instructor, which was kind of cool. To answer your question, how do you incorporate benzenes into medicine? So, excuse me. We say in this class that benzenes aren't very reactive. And while that is true, that's sort of a generalization, because you've probably heard that benzene is a carcinogen. Well, if it wasn't reactive, why would it be carcinogenic, right? And it turns out that benzene is actually fairly reactive, but only under specific conditions. And we really explore those conditions in this class very much. But if you have the correct conditions, such as having like an appropriate catalyst that's an electrophile, or a really, really, really strong base would probably do it. Not hydroxide, you have to get stronger than that. But there are ways to make reactions occur with benzene, and you can turn benzenes into phenols, or you could turn them into alkyl halide benzenes, or whatever. And then from there, they become more reactive, and then you can incorporate them into medicines however you want to. Generally speaking, though, if there are molecules out there that already have benzene rings in them and they're closer to the starting material than we are, we just use those. So a lot of doing chemistry is not necessarily just how do I construct everything from just carbon. A lot of it is how do I use these starting materials that other things have produced, such as like plants or enzymes or bacteria or whatever. And then what can I do with those molecules? In fact, as a graduate student at UW, one of my projects that I had to write a paper on was how to use bacteria to break the bonds in a molecule. And so I talked about how like flame retardants have like carbon-bromine bonds, and flame retardants are everywhere. Um, your couch probably is full of polybrominated flame retardants. And so I proposed, hey, I found this bacteria that eats carbon-bromine bonds. How about we just mix that in and then maybe throw it in a landfill, and then there won't be as many carbon-bromine bonds out there, which are toxic to most other organisms. And they love the idea. They thought it was super simple, though. Like, this is creative, but couldn't you do something a little bit more complicated? And I was like, no, I'm not a biologist. I know nothing about fucking biology. They gave me a pass anyway, so that's what's important. All right, let's talk about cyclic ethers because these are going to show up a little bit later when we talk about carbohydrates. These names are going to be common later. We're going to talk about furanoses and pyranoses. You don't need to know these structures. You just need to remember that when I say, hey, remember what furan and pyran were before? They look sort of like this shape. The important thing I would say about this slide is that if you have a ring structure and one of the atoms in that ring is not carbon, then the term that we call this is heterocyclic rings. So for example, benzene, oops, I didn't mean to do that. Benzene is a heterocyclic ring because every atom in, or I'm sorry, benzene is a homocyclic ring. Because every atom in the ring structure is carbon. And we've been abbreviating it for so long, but everything's a carbon. But if you change one of those things to something else, now it's a heterocyclic ring. Commonly, you're going to only see oxygen and nitrogen as the heterocycles in your rings. Nitrogen is super common. In fact, I would say nitrogen is way more common than oxygen. All of the interesting chemistry occurs because of nitrogen, because it can make 3 bonds, whereas oxygen only gets 2, based on the number of valence electrons it has available. So we're going to come up again on heterocyclic rings, probably when we talk about... when are we going to talk about heterocyclic rings? Probably not until the very, very end of the class. We talk about DNA. Because when we get to nucleic acids are all heterocycles. But carbohydrates are, well, carbohydrates are heterocycles also, I guess. They're just not, they're not aromatic. So, yeah, we'll talk about this again at carbohydrates. Okay, and again, ethers don't really do anything. So, ethers are soluble in water because they contain O, so they can hydrogen bond with water. They won't hydrogen bond with each other, so their boiling point is very low. Essentially, the boiling point of an ether is similar to that of an alkane. And then, like we said before, ethers go boom. So, yeah, that's it for ethers. Not really much to say, other than just, like, share stories with you and burn time, I guess. And ethers, apparently. So, let's get to the meat of the chapter. This is the actual important stuff today. Alright, aldehydes and ketones. These are important functional groups, so... Let's talk about what an aldehyde and a ketone are. So both aldehydes and ketones are going to involve this functional group. I'm just going to put question marks here because what goes in the question marks is going to change. But if you have a C double bonded to an O, this is called carbonyl. That's not how you spell carbonyl. I'm spelling it like someone from New Jersey would. A carbonyl. Maybe that would be someone from Australia. I don't know. Hey, mate. Got some carbonyls there. I apologize to any Australians I may have just offended, but whatever. Your accent is awesome, by the way. So, what does the carbonyl group do? Well, it turns out it's really reactive. And depending on what else is attached to it, we can do all sorts of crazy things. So, the focus of the rest of Chapter 14 is going to be, what are these sorts of crazy things that aldehydes and ketones do? We're going to look at some of them in great detail, and then we're going to sort of gloss over the other ones, but just show interesting consequences of them. Like the Tollens test and the Benedict's test. where we oxidize these things and we get pretty colors. We'll talk about those a little bit later. So, depending on what's attached to your carbonyl group, you're going to have either an aldehyde or a ketone. So, this that I'm highlighting right here in yellow is the carbonyl. We'll highlight this here. And then whatever is attached to your carbonyl is going to tell you what's going on with that group. So what we're going to do is we're going to look at one of the groups and check to see if it's H. If it's H, it's called an aldehyde. If there are no H's attached to the C double bond O, it's called a ketone. Now, there is another way to think about this. I'm going to draw it in a picture here. Hopefully my advisor doesn't find my lecture stream here. So if Karen is out there watching... Yeah, my advisor literally was named Karen, which is kind of funny in today's meme culture. But if Karen's out there watching me give a lecture... Sorry, I almost blew up your lab. If you have an aldehyde or a ketone, its position will actually just matter based on where you find it. So if this is my backbone, and I put my C double bond O over here, it has to be an aldehyde, right? Because there's the only thing that could go over here would be H. The ends of the chain. And alternatively, I could put one over here. So this would also be an aldehyde. But if I were to put this double bond anywhere else, such as say here, there's no way I can put an H on this because this bond is already attached to a carbon, and this bond is already attached to a carbon. That's all 4 bonds. Everything is tied up. So anything in any of these positions that is not on the end will be a ketone. Likewise, if I have a cyclic molecule and I stick a C double bond O on there, it can never be an aldehyde because aldehydes require an endpoint, and cyclic compounds don't have that. So cyclic carbonyls are always going to be ketones too. So you can really just tell whether a molecule is an aldehyde or a ketone by looking at the structure and seeing where along the chain the C double bond O is. Most of the time, you're going to see structures where this isn't even filled in. So if you see this just weird terminal C double bond O, that's an aldehyde. I don't know why, but when I look at aldehydes, they look weird. And so I see this and I'm like, oh, why did it just end like that? Oh, it's an aldehyde, that's why. So that's how you visually identify them. All right. Now, how the heck do you name aldehydes or ketones? It turns out it's super easy. We're going to just apply the alcohol rules and just instead do it for aldehydes or ketones. Now, with aldehydes, the aldehyde always has to be at an end, right? So the end is going to be 1. So that makes numbering super easy. Even I can't screw this up, right? So if I have a molecule like, say, this... and I fill it with fluorines over here to try and trick you. Be like, haha, they're going to put a bunch of 1s there. Nope, you go like this. 1, 2, 3. So, oh, I've inadvertently made something that could be offensive here. So this would be 666 trifluoro. And then whatever this aldehyde would be called. So I'm actually going to write the name for this. So this would be hexanal. The al is for the aldehyde. Now, very important, under no circumstances, when you pronounce this name, should you say the last 4 letters together? This is not hexanal. Tee-hee, there we go. We can all laugh. Oh, he said anal. Like, yeah, aldehydes end in anal. And we don't pronounce it that way. It ends in al. Kind of like, well, I mean, he's not our dean anymore, so I can't really make that joke. So this would be pronounced trifluorohexanal. I know it sounds really stupid, but that's how we name aldehydes. Okay, let me get that off the screen there. I inadvertently just threw 6s everywhere, so let's see here. Let's do more examples here. Here's one that doesn't have any weird functional groups. Remember, always just look for this. That's going to determine where your numbering goes. So if I was going to number the carbons here, I would number them starting here. This is always number 1. And so because there are 5 of these, this would be a pentane, but it's an aldehyde. So we go pentane, but instead of writing E, I write al for aldehyde. So this is called pentanal. Oh my goodness, I can hear her from here. What do you want? What do you want from me? Oh, Maya. She's being distracting. I'm like, should I squirt her with a squirt bottle? But I don't want to. All right, we'll see if I can focus. So naming aldehydes very straightforward. Let's have you try this. What would the name of this aldehyde be based on what you see here? While you answer that, I'm going to pet the cat so that she stops. Oh, she did stop. Now she's just grooming herself. Oh, she's paying attention. Go ahead and name this. I'll be back. Yep, that looks good to me. So we would number it 1, 2, 3, 4, 5, 6. Uh-oh. I guess it's not penta now. Unless I miscounted, right? 1, 2, 3, 4, 5. Yeah, so not penta now. You have the right numbering, though. So 3-chloro. And then this would be hex and al. I don't know if I have an example of this coming up, but just because we'll get it out of the way here. If you ever have this sort of thing, so I'm going to write its name on the board here. I'm going to let you imagine the name for yourself. And then I'm going to say the word butanal. Was that the word that you thought of? Butanal? Okay, good. We got it out of our system, right? Yeah. God, chemists, why? Chemists are really bad. And I 100% guarantee that this was not because chemists were trying to make a joke. This is chemists just making a system and then not realizing it after the fact and going, wow, we literally made a system that named our molecule but anal. Who didn't proofread this? Thompson, was that your job? No, I was assigned ketones. Oh. Ah. What a shitty naming system, huh? Do 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 do. All right. Please remember this lecture when it's time for course evaluations, I guess. I don't know. All right. So here's some more aldehydes for you to name. I did give you a butt anal. There it is right there. It's this one down here. So this is how you learn, right? I had to make really stupid jokes about stuff, and then you'll remember, wow, I'm never gonna forget how to name aldehydes because of butt anal, right? Like we'll always know that one. But go ahead and name these aldehydes based on what you see. We'll go over the answers in just a second. All right, one more minute to name them. All right, so let's name these aldehydes here. So I think the hardest part about naming aldehydes is trying not to laugh, for one. But for two, remembering that this is a carbon. So down here, this is a carbon too. It's easy to skip that carbon. So be really careful that you don't forget that that's there. So this would be propanal. Or propanal, I guess. Which really changes King of the Hill a lot. It changes the tone of the whole show. And then over here, 1, 2, 3, 4. So this is a methyl group. This is a methyl group. Not methyl. There we go, methyl. So this would be 2, 3. Dimethyl. Man, my handwriting in PowerPoint for some reason is just awful. 2, 3 dimethyl butanol. There we go. Maya has decreed it is time for a break. Oh my goodness. Yeah. Alright, so we're going to take a break before we talk about ketones here. I didn't mean to escape there. I need to go here. Alright, so I guess I have to go pet a cat for 10 minutes because that's what I get to do for my break. So let me start this. We'll get the Stardew Valley music going here. And I'll see you in 10 minutes. Oops, I didn't get water. I was sitting here chatting with people. Not you guys. I chat with other people. So I'm going to go get more water. And I'm going to just do this. Oh, it reset. Never mind. We'll just do this. Class will reconvene soon. Oops. And I'll be right back. There we go. I now have water. Now I gotta fix this, though. There we go. Alright, so we've named aldehydes and groups coming off of them just kind of like we named alcohols. Ketones, same thing. With ketones, there is a small amount of consideration for shorter chain ketones. For example, these two specific examples, you cannot have the carbonyl group be anywhere other than the position that is shown. So, let me get the red pen out here. So here, there's obviously only one central group. So propanone is the simple... Oh my goodness, hold on. Okay, we're done here, Maya. Goodbye. She wants me to pet her, and I have to work, so... She gets the squirt bottle. Alright, so for propanone, there's only one position that this can be in. It's in the middle. For butanone, there's still only one position, and that is on carbon number 2, right? Because if I put it over here, this would be carbon number 2. So no matter how you spin it or put it on a 4-carbon chain, you're always going to have your double bonded O be carbon number 2. So putting the positions of these... Oh my goodness. Please leave. Sorry, my cat is now just like, has a vendetta against me or something. Anyway, these are simple ketones. How do we name a ketone? You're going to name it like it was an aldehyde, except instead of putting al at the end, you put one. And that's how you name a ketone. For these simple examples, this is the only way that you can put them. If you have a longer chain, then you got to number where the C double bond O occurs. So for example, if you had a 5-carbon chain here, then what we would do is, that's the eraser, that's why it's so big. So if I did something like this, 2, 3, 4, 5, and I went like that, then now I have to number the carbons. And if I were to put it over here, it would be different than if it was over here. So I do have to indicate where it is. Like this. So this would be 2-pentanone. Kind of like how if this was this molecule, it would be 2-pentanol. Same thing. Now, the alternative naming scheme does exist. Just like, remember how I said that there was this scheme where we stick the number in front of the all? We're not going to use that, but it does exist, and it also exists up here for this. So this is the primary scheme that we're going to be using, these. This is just an alternative that you might see, and you do not need to learn if it looks confusing to you. All right. So any carbonyl that is on a chain that is longer than 4, so 5 or more carbons, requires us to put a number for the carbonyl. Just like our alcohols, just like our aldehydes, just like our cyclic functional groups. You obviously want the lowest number possible for the important group, and in this case, that would be this carbonyl. So we need to put the lowest number on this. So I would number from this direction, because going the other way, I would put a 4 there. So this molecule would be 4-methyl 3-hexanone. And that's naming ketones. Easy as that. So I'm going to give you this one. I want you to tell me its name. So type it in the chat when you think you have it. So those are really close. There's like 1 or 2 letters missing in the pentone part. What could you do to make it sound better? Or to be correct, I guess. But so here's what I was trying to get at. I want to write in this color, so So when you find the longest chain here, oops, I should number it the correct direction here first. When you find the longest chain here, and you write its name, if you have an aldehyde or a ketone, then what you do is you get rid of the E at the end. And then you add whatever the prefix is. So in this case, this is a ketone, so we would go "-one". So this would be pentanone. That's also how we get but-anal here. So if I had butane and I get rid of this, then it goes butanal. So that's what our spelling convention is. I probably mentioned that like just saying it aloud, but there it is in writing, so everybody knows. So what would the name of this molecule be? So I have a chloroate group 2, and then my ketone occurs at position 3, and it's a pentane chain, so pentanone. There you go. So it'd be butanone for a 4-carbon chain. And so that should be right there. Yeah, there it is. Or but a none or something. I don't know. Yeah, ketones end in "-one". Or known, I guess you could say. All right. Hey, look at this weird ketone. What the heck is this? It's like a circle. Any idea what this one would be called? I'll let you try it. All right, let's go around the ring. Do 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 do. All the way around. So we got. Now, if I go the other direction, I'm going to get the same groups because it's totally symmetrical. 357 trimethyl. And then this is always going to be at position 1, isn't it? Because that's how we define it. So I don't even need to put the 1 in there. So we'll just call it cyclo-oct unknown. Kind of like how with phenols, the phenol OH group always wanted position 1. And we just never included one phenol because it's always going to be that way, right? We've oriented it such that that has to be the case. All right, so here are some more. You're going to notice that like these cyclic ketones often look like people. In fact, I'm going to show you a class of molecules. I want to say that they're called the like puritans or something like that. But they just look like people, these structures. So this molecule looks like strong sad or something from Homestar Runner, I guess. I don't know. Anyway, try and name these ketones based on what you see here. We'll go over the answers in just a bit. All right, 1 or 2 more minutes to finish up. All right, let's go over the names of these. So I got a number from left to right here, obviously. 3, 4, 5, 6, 7, 6, 7, 8. Yeah, there we go. And then, so this is an isopropyl. And then this is a methyl. So this left one would be, let's see, isopropyl comes before methyl. So 5 isopropyl, 6 methyl, 2 octanone. And then for the next one here, this has to be position 1. And it's symmetrical, so I can go either direction. So this would be 2, 4, 4, 6. Tetramethyl. Cyclohexanone. There you go. Looks like those are the same answers that people got. So that's great. All right, any questions, let me know. All right. On the next few slides, I have some just descriptions of really common aldehydes and ketones. The most common aldehyde by far is formaldehyde. Formaldehyde is a disinfectant because it's very reactant, or very reactive. Basically, you use it for the preservation of tissue. You use it to sterilize stuff. It's quite toxic. Yeah, that's formaldehyde. Formaldehyde is very simple. Acetaldehyde, which is that on the next one? That's acetone. Okay. Acetaldehyde is this. This one's also common, so this is acetaldehyde. Although its correct name that we would name it in this class would be ethanol. And the only reason that I bring this up is this is the hangover molecule. What your body tries to do when it finds ethanol in your body is it will oxidize it. And as we learned in a previous section, when we oxidize primary alcohols, they become aldehydes. I need just a second. I'll be right back. Sorry, I could hear her meowing in the bathroom, and I'm just like, oh, stop. She's being real annoying today. What do we want to talk about? Acetone. Acetone's the simplest ketone. So its proper name is propanone. We showed this on the previous slide. Nobody calls acetone propanone. So if you see acetone at the store, this is what you're buying, and it's commonly used as a solvent to dissolve things. So nail polish remover will dissolve in acetone, but it won't dissolve in water because nail polish is a little bit nonpolar. Acetone is one of these weird molecules that just happens to be right on the line of things that are polar love it, things that are nonpolar love it, everything dissolves in it. So acetone is great for being a solvent. On the screen here, you're going to see a bunch of molecules. These are a family of molecules called hormones. And what hormones are steroids that serve specific functions. So these molecules here, so this is testosterone on the left, and you can see that testosterone ends in the suffix -one that we've been talking about all day. So it must have a ketone in there somewhere, and sure enough, there it is. Progesterone ends in -one, and sure enough, it also has a ketone. In fact, it has two. So if you hear the term -one in a molecule, like it ends in -one, it's because it contains a ketone. And then here are a bunch of molecules that I just threw in here for fun. For no reason other than that you can make molecules that look like people. And that this chemistry actually up here, we're actually going to do this reaction very shortly to discuss how you could take the part with the double O's there and you can replace it with any part that you want. Particularly my favorite is the Texan, because that's just silly. But anyway. All right. So we're getting close to the end of the chapter. We're probably not going to finish today, but we'll finish tomorrow for sure. And we're going to cover a few reactions here that are new, but a lot of the reactions I'm going to show you are kind of old hat. So you just have to remember that all of the stuff from before still applies. So find that sheet with all the reactions that you've been writing down. And here we go. So let's get all the physical property stuff out of the way. When you look at aldehydes and ketones in terms of their physical properties, they are capable of receiving hydrogen bonds. So this is going to be R or H, and this is just going to be R. So I could hydrogen bond from water here. That would work, but this molecule itself cannot hydrogen bond back. So aldehydes and ketones tend to be very soluble in water. However, because all they have is a dipole, so this carbon is not as electronegative as this oxygen, which is very electronegative. So there's a permanent dipole in this molecule. Polar molecules will stick to each other like they're tiny magnets. So the boiling point of aldehydes and ketones is higher than that of alkanes. But it's lower than that of alcohols. So that should have been THAN, and I messed up at the end there. And so if I go alkane, aldehyde, or ketone, alcohol. So there's my boiling point ordering right there. Now, remember, why do alcohols have a really high boiling point? Because they can hydrogen bond to each other. So they stick even better to each other and prevent boiling from occurring. Gotta remember our intermolecular forces. All right, here are some numbers for you to see. You can see that I am putting aldehydes and ketones just as approximately equal to each other because they don't differ by that much. Typically, aldehydes are a little lower in boiling point. However, they are so close that on a test, I'm just going to have you arrange them to be similar, or I will just ask you one of them. All right. And then there's our polarity that I've shown. We already talked about hydrogen bonding, so wow, I really preempted all my slides here. Good job, me, I guess. I don't know. Okay. All right. Do we remember how to get aldehydes and ketones out of alcohols? Hopefully we do. Remember that if you oxidize a primary alcohol, you get an aldehyde. If I oxidize this aldehyde, here's my aldehyde right here, and the O just hops right in, and I get a carboxylic acid. So that's what this is. We're going to do carboxylic acids in chapter 15, the next chapter. So this slide should not be new. Aldehydes get oxidized to become carboxylic acids. Likewise, earlier we said that when you oxidize a secondary alcohol, you get a ketone. But if you try and oxidize a ketone, nothing should happen because there's no H by itself for you to sneak an O in. So you cannot oxidize ketones. Ketones are just stuck there. Now, what would happen if we tried to do the opposite of oxidation? What is that called? Oh, we're not doing that yet. We're not doing reduction. I guess we're doing Tollens and Benedict's test. So keep that in mind. Yeah, we're going to do reduction. We're going to do a reduction test later. Reduction is just the opposite of oxidation where you add hydrogen instead. So I put H in a bracket. And you just undo what oxidation would do. These tests that we are going to show here in a second are actually reduction tests, but they don't follow the same rules as with H2. Instead, they just give us unique results and make a mess in terms of organic chemistry. So we're going to look at these next few reactions in a little bit of a special case. And so what we're going to do is we're going to look at these solutions called, oh, maybe they are oxidation tests. I'm thinking, hold on. Oh yeah, silver definitely oxidizes. What about copper? Is it copper one? Maybe, I don't know. I'll have to look up the reactions for Benedict's reagent, but I was just surprised to see this word here, because... Anyway, don't worry about that for now. So what we're going to look at here, we're going to look at two different tests. And so here are what the tests are called. So the first test that we're going to look at is called Tollens test. That's not an apostrophe. That's just a mess. And yesterday, I believe it was, I was talking about how we do a test to make a silver mirror. The Tollens test is the silver mirror test. And then there's another test called Benedict's test. And basically, you're going to turn a blue solution of copper into a red one. Now, these tests that we're going to talk about, Tollens test and Benedict's test, only create obvious results for very specific conditions. So, now, which aldehyde and which ketones get oxidized depends on the reagent here. So, it says right here, oxidizes the aldehyde, but I'm going to add right here, specific, just so we don't get mixed up. So Tollens test oxidizes all aldehydes, but Benedict's test does something totally different. So I just don't want you to get mixed up when we talk about that. All right. So here's what Tollens test looks like. I'm just going to skip over this slide for now. to just sort of explain. So Tollin's reagent is a silver ammonium basic compound. That what it does is it changes the... Sorry, my pen is not working here. Then it was working, and then it sort of colored everywhere. So it changes the aldehyde into what's called a carboxylate salt. And in doing that, this silver right here, which is actually silver plus 1, becomes silver with no charge on it. Now, we sort of don't really care about all of this miscellaneous crap that's going on. What's important is the thing that's been boxed in blue here. Doing this reaction in the presence of an aldehyde makes silver metal. What does that mean? That means that if you have an aldehyde and you add Tollin's reagent to it, you produce silver metal. What does silver metal look like? Well, if you have a very thin layer of it, it looks like a mirror. In fact, silver mirrors are made using this method. Do I have a video of this here? Because it's really cool. So we're going to show this. I need a new window. YouTube. All right, here we go. So, window capture. So, let's do this, and then we'll make it bigger. All right, so I already have one reactant in there. That's the aldehyde. I'm going to take the Tollin's reagent and pour it in here, and here is what happens. This is not me doing the reaction, but... So you'll notice that it will get dark after a while. But then, when you swirl it around the sides, look at what happens to the sides of the flask. Like, it looks like it's getting darker, right? Like, something's definitely going on there. Until you stop shaking it, and then you notice, like, oh, I've basically made a mirror. In fact, if you look carefully, or if I pause the video here, you can now see the experimenter in the reflection of the glass, whereas when we started doing this, you could not. And this mirror gets brighter and brighter and brighter and brighter the more you do it, and there you go. Now you have a perfectly reflective mirror in the thing, and now he's waving at you. Now, how do you clean the mirror off? You basically have to scratch it off. So this is a one-time experiment. Nobody wants to sit there and redissolve the silver mirror. Although you can. You can oxidize the silver, and then the silver is dissolved, and you can recover it that way. But that's how mirrors are made, is they do the Tollin's test. All right. What does the previous slide say? Oh, it's just saying what I said earlier, so that's fine. So, Tollin's test detects any aldehyde. That is the only thing it detects. So if you have a ketone and you react it with Tollens reagent, nothing happens. You get no reaction. So your goal when looking at a problem and me asking you, does this react with Tollens reagent, is going to be to just find the aldehyde. Is there an aldehyde anywhere on the molecule? It doesn't even matter what else the rest of the molecule is. The answer is yes, it will react with Tollens. With Benedict's test, which is the next one, what we're going to start with is a blue solution of copper 2. Oh, it does get oxidized to copper 1. Okay. When you react copper 2 ions with your specific compound, certain aldehydes are ketones, and I'll highlight that. So certain ones. We're going to show the certain ones on the next slide. You get copper 1 oxide, and copper 1 oxide is bright red. So the positive for this test is it turns red, and the negative is that it stayed blue. Where'd my pen go? There it is. I couldn't find the cursor. All right. And again, I have to write down here specific, because not all aldehydes get detected. What aldehydes or ketones does Benedict's reagent detect? Here are the 3 orientations of molecules that Benedict's test will find. So what are these orientations? So this is aldehyde next to ketone. So here's my aldehyde right here, next to a C double bond O. We have aldehyde next to alcohol, or ketone next to alcohol. Either of those will work. So whenever you're given a molecule and I ask, hey, does this react with Benedict's reagent? You have to look for these structural features. Do you have 2 double bonded COs next to each other? And one's an aldehyde? If so, it reacts. Do you have an aldehyde next to an OH or a ketone next to an OH? Those both react too. All right. So now the questions are going to just be like this. Which of these molecules react with what? So for example, here I'm going to ask you about Benedict's reagent. I want you to tell me yes or no strictly on Benedict's reagent. But on an exam or a quiz, what I would ask you is, here are some molecules. Will they react with Tollens, Benedict's, both, or neither? Okay, so go ahead and answer these from the perspective of what the question is asking here. So will these react with Benedict's reagent? If you don't remember what the molecules the Benedict's reagent reacts with are, go back to this previous slide right here. All right, I'll give you 5 or so minutes to go over the answers. And then I believe that's all we're going to do today. This will be all finished. So see you in a bit. All right, let's go over the answers here. I get to the right screen here. So let's look at number 1 here. So number 1 will react with Benedict's reagent. So Benedict's reagent will react with aldehyde next to ketone, aldehyde next to hydroxide, or ketone next to hydroxide. I only just have the aldehyde here, so this is going to be no. So we'll do Benedict's no. How about over here? I can't do any of the aldehyde things, but I can do ketone next to alcohol, so this works. So for Benedict's, this would be yes. And then over here for this third one, I have aldehyde next to ketone, so this will also work too. Now what I'm going to do is I'm going to do the following here. So let's go to the felt tip pen. And we'll go like this. I messed up. Hold on. I can't get it to click. There we go. There we go. Now do the question again. I want you to answer this question. Which of these will react with Tollin's reagent instead of Benedict's reagent? Okay. So I'll hit mute again, and we'll come back and we'll go over the problem with looking at it from Tollin's reagent. All right, one more minute to figure out which reactions will occur for Tollin's here. All right. So remember that Tollin's reagent reacts with only aldehydes. So you just got to look for an aldehyde, and if there's an aldehyde present, then yes, it'll react. So here's an aldehyde right here. Well, this anyway. So Tollin's will definitely react with that. Number 2 does not have an aldehyde. It has a ketone and an alcohol, so nothing happens here. And then number 3, there is an aldehyde next to a ketone, but really all we care about is this part. Now, if you look carefully, you'll notice that we have different results for both of these. So, by using Tollens and Benedict's tests together, you can identify a whole bunch of different molecules from each other, which is super useful. So these tests are often used in tandem. There are other chemical tests that you're going to see in the carbohydrates lab, as well as the whatever lab 3 is called. Lab 3 is basically kitchen sink of molecules. We just throw everything at you. All right, so that's how we use Tollens and Benedict's reagents to identify stuff. You're just going to be responsible for telling me, does it react, yes or no? You do not need to know the chemistry that's on the slides here. So like when I show you this reaction right here, doesn't matter at all. The only reason I showed you that is to show, oh, we made silver metal. That's where the mirror comes from. So again, just tell me yes or no. All right, that's all I got. Any questions, let me know. We are done here for today. There are some assignments that are due very shortly. Later tonight, I will send out the straw poll once I get it done, because I have to do that for another class. I might as well do them both at the same time. And exam number 1 will be coming up pretty soon. That's right. So Tollens is positive if there is an aldehyde present, negative if there is not. And that's all that Tollens cares about. All right. We all set? We all good? Any last questions? Let me know. Hooray! Okay, I guess I'll hit this music button then. I'm going to go figure out what my cat is doing now. Have a wonderful rest of your day. We'll see you tomorrow.